Next presentation is on a pretty interesting technology. This is a presentation that really Eric Dollard should be presenting. Due to some medical complications, he wasn't able to make it up to the conference this year. And Eric will be okay. It just takes, there's some stuff that we're going to be helping him with. I'm going to be doing the first half of the presentation, which kind of gives a background on this. And then what Eric did was he sent me about, 15, 17 slides of all the equations. And I had maybe a couple days to understand all of it and present on it. That's not going to happen in this lifetime or the next. So Eric is going to be patched in on a phone, and he is going to be explaining the diagrams, the equations, the math as it applies to this technology, how it shows up in a patent that came out later on, what the inventor's math shows, and I just realized that we never pulled the equations out of the patent, but that's okay. So this presentation, okay, and then after Eric kind of goes through that, he's going to show a couple power curve graphs, and then after that I'll do a demo. Everybody pray really, 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 really hard that that thing actually spins and has some semblance of what it's supposed to do. So this presentation is called The Law of Electrostatic Induction as Applied to the John G. Trump Electrostatic Machine. And this goes into concepts dealing with parameter variation. That's kind of, I believe, kind of an advanced subject in electrical engineering and potentially has results that are, not supposed to be possible. So as Eric and I co-present this, I'll do the easy part and he'll do the more difficult part. I do want to mention Eric's, the organization is EPD Laboratories, Inc. It's a 501c3 nonprofit in Nevada. And on ericpdollard.com, that website right there, if you go there and in the right column and you scroll down, there's a link where the whole organization survives by donations. I've also put a significant amount of funds in that direction out of my own pocket to support what I can. And also, there's been people who donate over the years. A couple times there's a big donation once in a while, and that helps out. And besides those donations, Eric lives off his Social Security, but he wants to see these projects move forward so fast and with people helping at the shop that he's also paying people out of his Social Security money. This is how bad he wants this to move forward. And, he shouldn't have to do that. And that's just how it is. We help out how we can. But if you go there, there's a PayPal link. And if you're able to make a donation, that goes right into the EPD Laboratories, Inc. PayPal account. And then also there's a mailing address in Spokane, Washington with the EPD name on it. And we can take checks, money orders, personal business checks, whatever. Every donation helps. And that's what kind of supports a lot of these projects going on down there, and with him being able to support us, how he's helping Griffin, Hakasez, myself, and a lot of what's kind of going on here wouldn't be possible without Eric's interaction, so it's very important. So part one, I'm going to basically go through the background of this electrostatic generator. This is a technology that I think is probably one of the most important technologies ever developed. Almost nobody knows about it. And for Eric to be that excited about this as one of the few things he really has a short-term focus on, that says a lot, because if he sees a lot of potential in this type of technology and what he's been figuring out and intuiting, then to me that means I need to pay a lot of attention to it. And I think a lot of people would agree. So the inventor of this machine, who knows who John G. Trump is? Most, probably 95%. So this is Donald Trump's uncle, Donald Trump's father's brother, John G. Trump, and let's see, he was so this is, I'm not going to read every single one of these, but this is some of the, right here, he's saying electrostatic forces can be maintained with no power loss. And so what that means, as it applies to the actual machine, is that if you have the electrostatic potential supply and you charge the rotating capacitor, if that's in a vacuum and ideally there is no leakage, this is the worst possible scenario, open air with a very old build with a lot of leakage. If this was the ideal situation, you could charge it once, remove that charge, and as the motor's turning it, it's kicking out a sine wave and powering a load, but the charge never diminishes on the cap because that's not where the load is being powered from. it self-sustains. That voltage just stays there. So it's already better than 99%, and in larger machines, it's better than 99%. So there's a lot of wording like this in the conventional stuff and patents. You know, they're not going to accept over unity claims or whatever. I remember in one of John Bedini's patents, it said 99% more or less. So this is, there's very few really good, there's almost no really good pictures of this, but this is one of the best. And basically you can see that there's going to be like a jar encompassing all these plates that are almost like bow tie kind of paddles, really, really big. And you know, they're drawing pretty serious vacuum on these and going way up in voltages. But this is kind of an example of what he was working with compared to this with a whole lot of plates, really small diameter and everything. The principle is identical, but this is flea power. We're talking about like under a watt output. But the thing is this is just a study tool for right now. I'm just hoping it makes it through the conference so that we can at least get the data to see what this is doing. Later we'll maybe do some, we want to put it in a vacuum, see how high we can get it, and so forth. So this picture right here is Eric Dollard and Chris Carson. This is at Santa Barbara Amateur Radio Club presentation, and that's the table that had some electrostatic stuff that Chris started to talk about, and then it just magically disappears out of the presentation and goes to Eric talking about the sun. Maybe about a week ago or something like that, I did a recorded call with Eric. I can't remember even how long it was, but I just wanted to get the recording of his story about how he met Chris Carson, and here it is.
We have Eric Dollard on the line, and we're going to talk a little bit about Chris Carson, how he met him, and how the whole electrostatic rotary converter project has been started. Years ago, Eric was one of the members of Borderland Research Science Foundation, and Chris Carson had been involved with them, and this was, I guess, maybe in the mid to late 80s. How did you know Chris before Borderlands, or did it come after? Or
no, it was, I think it was Peter Lindemann had come out to the Integratron.
But when Chris had built that, did he do enough experiments to come to any conclusion or anything?
Yeah, he had... He was saying that he had observed various things, you know, like the fact that it maintains its excitation without, you know, a continuous supply of current. I remember him remarking about that. And it was quite a setup. He had, you know, all these high voltage diodes and microamp meters and what have you. When he got into experimenting, it got quite involved. But then at that point, he had become absorbed into this situation that I just described, and we no longer interacted with each other.
Mm-hmm.
And that was about the time a lot of bad things happened then. The vault died. I was kidnapped by some people in Montana. Lockwood died. Chris died. It all happened within 45 days, and my whole world just crashed to the deck.
And you mentioned that you and Chris had found that there were, as you mentioned, some commercially available electrostatic rotating machines, 5 kilowatt level. And I don't know if they still are in production or what, but you know, we've done some searches and can't find anything.
Yeah, I don't know, but I remember a picture of it in my mind when he showed me that he had found, you know, information, some article or a paper or something on a machine that produced, I think, 5,000 watts at 100,000 volts, was in some kind of pressurized vessel, and it was a spinning variable capacitor. So that was enough to make it look like it was worth pursuing. Okay, so this is output versus excitation potential. So as the excitation potential, or charging voltage, as you may call it, is increased, the electromotive force pretty much goes up in proportion to that, but the power goes up in proportion to the square. So that's good. So we can see once you start getting past 3 kilovolts of excitation, the thing starts to take a pretty steep climb. In this case, 140 milliwatts would be what we would expect at 3,000 volts, with, as of yet, an indeterminate leakage conductance or load resistance, or however you want to look at it. So here the machine is producing almost 600 volts with a load resistance of 2 megohms on the output of the transformer. Okay, the next diagram or drawing. Okay, so this is basically the output power versus load resistance. So we can see as the load resistance increases, or more properly, as the load conductance decreases, the electromotive force on the secondary basically goes up in a logarithmic fashion. So a curve like that indicates that this machine is a constant current device, unlike the electromagnetic machines we're used to, which tend more to be constant potential devices. So the question then is what load consumes the maximum amount of power for a given amount of excitation and RPM, which are fixed in this case, and that turns out to be actually quite low. I was surprised that it's in the vicinity of about 3.5, maybe 350 kiloohms. So this again would be kind of indicative of a constant current machine. Is the more that you load it down, the more power you're going to get.
I just had to use what I have on hand, and like Eric said, you'd need a custom transformer, exactly tuned for this application, or other method to get the voltage out of the machine. That's on a 1x scale right now. It's 352 volts peak to peak at a frequency about 217.